Hey everyone, welcome to your play pause it for the day. We are going to be covering different types of lines and then wrapping up the triangle sum theorem that we started last class. So go ahead and grab your notes, grab your OHS play pause it graded assignment, have that open, and we'll get started. So a few quick review items just so we can kind of keep fresh. The last thing that we did together were parallel and perpendicular lines. So you guys remember parallel lines have the same slope, right? And they're never going to cross. Their slopes are the same, they're equal. So here's a question pulled from one of the previous actual SOL tests. So you could see a question like this. The graph of the line J is shown. So it gives us a line here on the graph. Which ratio or fraction represents the slope of a line parallel to line J? So we first need to remember, okay, they're looking for a parallel line or a parallel slope. That means I'm going to need to have the slopes be the same. They're going to need to be equal. So first, let's find the slope of this line. Now there's a few ways to do that. We can use the slope formula, right? The change in y over the change in x. It's a subtraction. You might see it written delta y over delta x. So you can use each of these coordinate points and find that slope. Or we can use the graph. Why not? And do rise over run. So 1, 2, 3. We rose 3 units. And we're going to run 1, 2, 3, 4, 5, 6, 7. So the slope of the given line is 3 over 7. So to find our answer, we just find the one that matches that, and that is A. Don't forget, I always myself forget to tell you this at the very beginning, but remember, you guys can pause this recording at any time. If you're watching the play pause it, the questions will sort of help pace you and pop up and do those pauses for you. If you're watching the ViewPure link, then you're going to want to hit pause occasionally so you can take notes and try the questions on your own. Here's the next one. Which graph best represents a line perpendicular? So just to review, perpendicular slopes are opposite reciprocals. Opposite reciprocals. So here's an example. If the slope is 1/2, then a perpendicular slope is going to be opposite in sign. So since this is a positive, we'll have a negative. And then it'll be the reciprocal. You flip the fraction. 2 over 1, the reciprocal. I'm going to grab a different color. Okay, so again, just like the last one, let's first find the slope of the given line. So here I'm going to count up 1, 2, 3 over 1, 2. Up 3 over 2. Up 3 over 2. We know it's positive because the line is going up from left to right. So that's just a good check that we know this is a positive 3/2. So the line we're looking for is going to have a slope of what? What is the opposite of 3/2? Negative. And the reciprocal is 2/3. So we need to find which one of these graphs matches with the slope of negative 2/3. Well, they're all going down from left to right, so we can't really eliminate any of them that way. So let's just check. We need it to be down 2 over 3. 1, 2 over 3. 1, 2. Oh, this one's very close, but you guys can see that that line does not actually go through that grid mark. This is not 2 over 3. Let's try this one. Down 2 over 3. Same. See how close that is? That is not going through the grid mark. Down 1, 2 over 3. Oh, same. This line is not intersecting there. So it must be D, I hope. Down 2 over 3. Yay! Right on that grid. Down 2 over 3. Right on the line. Perfect. The answer is D. So usually the first step with all of these is to find the slope of whatever's given, whether it's 2 points or a line, and then either match it up with the same slope or find the opposite reciprocal. Here's the other topic we've been doing recently with parallel lines and transversals. So I don't have this indicated here, but we're going to say that line A, actually, hold on, we're looking at the converse here. So this is good. This is the very last thing we did. It says if the measure of angle 3 is congruent to the measure of angle 7, then which two lines are parallel? So this can be kind of tricky because we have 4 lines here, right? And they're making those 4 groupings of angles. So we wouldn't say like line A is parallel to line B because of this, right? Because these two angles, they don't even touch angle B. I'm sorry, side line B. Angle 3 and angle 7 are nowhere near line B. So those have nothing to do with line B. They're only touching line C and line D. Those two angles are on line C and line D. And A happens to be the transversal in this case. So if those two angles are equal, then we know lines C and D are parallel. And I chose C and D again because those angles live on those lines. We have nothing to do with B here, nothing. So the reason would be what kind of angles are those? And those are corresponding angles. They're in the same position. Depending on how you're looking at it, if you're looking at it the way it is right now, then I would call angle 3 sort of the bottom right and angle 7 the bottom right. Right? So these are corresponding angles. And you could be more specific if you want, and you could say corresponding angles are congruent. All right, let's look at the next one, number 2. I'm going to get a different color so we can sort of start matching this up because I'm sure we're going to have lots of angles here once we get done with this all. So angle 14 and angle 4. Aha. So again, these two angles have nothing to do with line D at all. They're not touching line D whatsoever. So the two lines that they are touching are line A and line B. So the yellow angles are touching those two lines. So those are the two lines that are parallel. And why? So C happens to be the transversal in this case. And so what kind of angles are these orangey angles? They are alternating and they are on the interior of those parallel lines. These are alternate interior angles. Again, you could be a little bit more specific and you could say, if angle 4 and angle 14 are congruent, then they are alternate interior angles, therefore lines A and B are parallel. All right, let's look at the third one. Angle 12 and angle 6. Angle 12 and angle 6. All right, where do they live? They do not live anywhere on line C, right? So we're not saying C and D are parallel here. Nope, because 6 and 12 do not touch line C at all. So we're looking at line A and B. 6 is on line A, 12 is on line B. So line A and B are parallel. We just have to figure out what kind of angles they are. What kind of angles are the red angles? They are on the outside of line A and B. They're on the exterior, and they are alternating across that transversal D. So these are alternating exterior angles. The alternating exterior angle theorem. So you see how this is the converse of what we learned the very, very first day. So this time we're looking at the angles and we're saying, okay, if that's true, then the lines are parallel. See, if those are equal, then. So let's look at number 4. This time we're going to look at supplementary. So if angle 15 plus angle 12 equals 180, then what? All right, let's take a look at where these angles live. They do not live anywhere on line A. Nowhere. So we're looking at C and D. 15 is on line C, 12 is on line D. So C and D are parallel, and B happens to be the transversal in this scenario. And we just got to look and say, what kind of angles are these? Well, they're on the same side of that transversal, right? They are on the inside of the parallel lines. We have an angle pair, and they are called, you can call them same side interior, or we call them consecutive. The consecutive interior. Kind of synonyms there. It kind of depends on which textbook you're using, which teacher you're talking to. I usually call them consecutive interior. They're one after another, but they also are called same side interior. And they are supplementary. Okay, last one. Measure of angle 1 is congruent to angle 9. Yeah, our picture is getting a little jacked up now. A little messed up here. Angle 1 and angle 9. Okay, where do these live? They live on line C and line D. We just have to ask ourselves, what kind of angles are these? And they are in the same position, upper left, upper left. So we're going to call those corresponding angles. And some of you might be saying, well, wait a minute. Angle 1 also lives on line A, doesn't it? And angle 9 also lives on line B. So couldn't we talk about lines A and B? And not really, because because if that were the case, then we wouldn't be looking at the right transversal. And maybe we'll talk more about this one in class, and you guys can sort of brainstorm and we can debate a little bit on this one. So remind me about that. All right, finishing up our notes from last class. So if you're following along on the guided notes, these are going to be the ones from our last live class on Thursday. We talked about triangles and how they form two different kinds of angles. The angles we're used to seeing, interior angles, those are the angles that are on the inside of the triangle. But if you extend the edges of the triangle, then some angles will also form on the exterior. You can see each vertex will form 3 exterior angles. So our blank here is exterior. And we're going to look at how to find the measures of interior and exterior angles. Our triangle sum theorem says that the sum of all 3 interior angles in a triangle is 180 degrees, always. So the measures of a triangle always add up to 180 degrees, no matter what kind of triangle it is. So we can find the value of x here because we know they're all going to add up to 180. And we can solve this for x. So we'll combine like terms. We got 6x equals 180, and then divide by 6. So x is 30. And that's what it wanted us to do, find the value of x. So we could stop there. Now, if you wanted to go further, you could certainly plug x into each of those angle measures, and we would get 30 degrees, 60 degrees, and 90 degrees. This happens to be a special triangle called a 30, 60, 90 triangle, and we'll learn a lot more about those in semester 2. So then let's talk about how to find exterior angles. Here's the theorem. It says that the measure of the exterior angle, like right here, is equal to the sum of the measures of the remote interior. So let me tell you what those are. The remote interior angles of the exterior angle are the 2 angles across from it. So in this case, it's angle B and angle A. If I had drawn my triangle this way, then the remote interior angles from this one would be these 2. It's the 2 across from it, not the one right next to it. It'll never be the angle right next to it. It's the other 2. So all you do is you add those 2 up. I'm going to call this angle B plus angle A. So let's do the example 1. To find the value of y, all you do is you take the 2 angles across from it on the inside of the triangle and you add them up. Y equals 88 plus 70. 158 degrees. That's it. And that makes sense, right? Because when you look at angle Y, it's definitely obtuse. It's bigger than 90, and the one next to it is super tiny. Let's do example 2. So we're going to say the outside angle equals the 2 across from it added together. So x plus 80. Now we just solve for x. So let's get the x's together. We'll subtract x from both sides. You get 2x minus 22 equals 80. And then we'll keep combining like terms and add 22 to both sides. And then divide by 2. So x is 51. And this one says find the measure of ACB. Interesting. ACB. Which angle is that? That's this one. Wants us to find the measure of that angle. So let's use the information we have. We'll have the value of x and can plug it in here. So this angle is 51. Now how could we find the measure of the teal angle? We know that all 3 angles in a triangle add up to 180. So if we have 51 plus 80 plus we don't know must equal 180. That's how you can do that. We could call this y if you want to, like another variable. So let's solve for this unknown. If 131 equals, 131 plus we don't know equals 180, and then subtract 131 from both sides. So this angle measure is, what is that? 49, is that right? Let's just confirm, because I did a lot of that mental math, like quick and in my head, and I don't want to give you guys any mistakes. So let's just check that really quickly. Okay, we're good. So I wanted to come back to example 1 really fast and talk to you about one thing. So we found the outside angle to be 158 by adding the 2 across from it. Any ideas another way to find the outside angle here? It might take longer. There's another way. We could find this angle, right? Because it's going to add up to 180. So we would do 180 minus 70 minus 88. What is that? Let's go to our calculator. 22 degrees. So this angle is 22 degrees in here. And then look, these 2 angles are on a straight line. Remember what angles on a straight line add up to? These also add up to 180. So 22 plus y equals 180. And we can solve for y. 180 minus 22. 158. Woohoo! It's the same value that we got by doing the exterior angle theorem. So you won't be able to do what I just showed you on all of them. Like we could not do that in example 2, right? Because we had too many unknowns. Like this was an x and we didn't know this one. But sometimes you can, like in example 1. So just kind of keep going back to what I told you guys before, that if there's more than one way to solve a problem, do the way that makes the most sense to you. Okay, it says find the missing angle measure. So this is like a puzzle. We're going to start with what we know and work our way through the diagram and find all the missing angle measures. So I see 2 triangles and we know these 2 angles. So let's find the third. Anytime you know 2, you can find the third. And we can set it up like this if you want. 14 plus 45 plus we don't know, we could call it x, equals 180. Or you can just take 180 and subtract out the angles, right? Same difference. This is a 14. Let's do that with our calculator. 121 degrees. All right, so this angle is 121 degrees. Now, look, we're going to use all the skills that have been building up to this. What kind of angle is right across from the 121? Starts with a V. These are vertical angles. Yeah, and what do we know about vertical angles? They are equal. So if that's 121, then this is automatically 121. Cool. Now we only have one angle left to find. That's angle D down here at the bottom. And we already know these two, so we can find it just like we found angle E above. We would do 180 minus 121 minus 27. 32 degrees. Little tiny angle. Not as tiny as 27. So see, hopefully, I know that I'm the teacher and I'm the one doing this, so it might seem easier than it should, but hopefully it feels easy to you guys. We're starting to bring in some skills that we already know, right? Those vertical angles, and then using basically algebra, right? Solving equations to find those missing angle measures. All right, we're going to wrap up other lines and planes. So we've already talked about parallel lines, and we've talked about perpendicular lines, but there are two other kinds of lines that I wanted to talk with you guys about. The first one are oblique lines. And here's the definition of that. In fact, why don't I type it for us? Because I can. And sometimes my typing is much better than typing. So oblique lines are slanted lines, and they are on the same plane. So we've talked about planes before. Planes are, it's just a space. Like the top of your table is a plane. It's a surface. It's a space. And if you have like a pencil on your tabletop and a mouse on your tabletop, then those two things are in the same plane. Oblique lines are not parallel and they are not perpendicular. So sometimes you'll hear teachers or other people, textbooks and other videos and things say that it's easier to talk about what oblique lines are not than what they are. So if the lines are not parallel and they're not perpendicular, then they're oblique. They're slanted lines on the same planes. We can draw a little picture if you want to. If I had a plane, let's say I have a plane like this. We labeled planes with large capital letters. And I did, let's see, that one and I don't know, this one. See, they're obviously not parallel because they're crossing, but they're not perpendicular. They're not crossing at a 90-degree angle. I promise you. Maybe I need to make that, how about that? That's a little bit better. So two lines on the same plane that are not parallel, not perpendicular. All right, the last kind of line we're going to talk about in geometry are skew lines. And, you know, we talked here that, I don't know if I said this specifically, but the only lines you can have in two dimensions are parallel, perpendicular, or oblique. That's it. Think about it. If you have a space, this two-dimensional space, you're going to either have parallel lines, you'll have perpendicular lines, or they'll be oblique. There's really no other type of lines you can draw. That's it. So skew lines exist, and let me type again. They exist only in 3 dimensions. You know, sometimes it's hard to visualize 3 dimensions in PowerPoint on a 2-dimensional space, but I do have a 3-dimensional diagram coming up for you. You probably see it in your notes. And the other thing about skew lines is that they do not intersect and they are not parallel. So if they don't intersect, oh, okay, well, let's just look at some examples of them. It's easier to see it, I think. Okay, but first let's talk about parallel planes. Well, maybe I can, here, let's do this. This is nice, this interactive Wait, let me bring this diagram over here to skew lines. You guys have it in your notes. So it's fairly close to where you're taking these notes. I just wanted to have it on my screen. So they exist in 3 dimensions. Here's a 3-dimensional picture of a cube. Let me get my pencil. So let's start. There we go. They do not intersect and they are not parallel. You see that? They are not parallel. So here's an example actually with the pink and the purple. Line CG, you can imagine, is sort of that front edge of the cube. And line EF, sort of that bottom edge of the cube. It's so weird how sometimes it looks like EF is the front and sometimes it's the back. It just kind of depends on what tricks your eyes play on you. But lines CG and EF are skew lines. They're in the same plane, in this case, a cube. They're not intersecting. So it might look like they're intersecting here because the lines are crossing, but you guys see they're not really intersecting, right? Because CG is in the front of the cube and EF is in the back. 2 lines that would intersect on a cube would be like AD and DC. See, like they're literally touching right here at point D. All right. So let's talk about parallel planes. So parallel planes in a space are exactly what you might think they are. They're just like parallel lines in 2 dimensions. So they do have the same slope and they do not intersect. And you can kind of, I'm gonna bring back my sandwich. I feel like I talk about sandwiches a lot in class. I don't know if that's in my algebra class too, but like you can imagine the blue square is the top of the sandwich, is A, B, C, D, and E, F, G, H is the bottom. Those are parallel planes. Those planes are never going to cross. The top of the box and the bottom of the box are never going to cross. They'll always be separated by these sides. So some examples, we can say plane ABCD is parallel to plane EFGH. There are how many more examples? 2 more examples, right? Like the front and the back of the box. They are surfaces of that box and they'll never intersect. So you could say DCGH, plane, is parallel to plane, that's the front of the box. The back of the box is ABFE. That's how my brain is seeing it. I understand that some eyeballs might see ABEF as the front of the box. It kind of depends. And literally the box is like bouncing back and forth right now in my eyes. I don't know if it's doing the same thing to you guys, depending on the perspective, how you're looking at it. Whether C is the front corner or E and F are the front. Ooh, that's strange. It's like an optical illusion. That's pretty cool. All right, so going with this orientation, the very last set of parallel planes would be what? Let's see, we did the top and bottom, we did the front and back. So then it would be the 2 sides, right? ADHE and BCGF. BCGF. And it doesn't matter what order you go in as long as you go in, okay, let me rephrase that. It does matter what order you go in. It doesn't matter where you start. So we could start with A and say A, B, C, D, or we can start with C and say B, C, B, A, D. As long as you go in order, it does not matter where you start with the letters. You wouldn't want to say B, D, A, C. No, 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 no. You have to go in order along the edges, but it doesn't matter where you start. All right, here's our last 4 examples. I'm going to get a different color. First one says name all the segments parallel to AD. We're talking about segments. So let's get a highlighter. Here's AD. All the segments parallel to that. So it will not cross right? Like DC would be perpendicular, right? Because it's connected there at D. So BC is another parallel segment. What about EH? Can put little segment bars above them to be accurate. And also FG. That's sort of like a diagonal. You can kind of look at it this way. There is a plane intersecting right through the diagonal of that box to make sort of two triangular prisms. Number 2, name all the segments perpendicular to AD. So we just talked about that. So that'd be DC. And what else intersects AD at 90 degrees? So many other things. AB and DH and AE. All right, number 3. Name all the segments skew to AD. So let's review what skew means. Not so bleak. Skew. They do not intersect and they are not parallel. They do not intersect and they are not parallel. So AD. So they cannot intersect, which means it can't be anything connected to it. And they're not parallel. Now my eyeballs are playing the tricks on me where the cube is like changing its orientation on its own. That is so strange. All right, so it can't be anything connected to AD and it cannot be parallel. So pretty much everything that we did not name up here. So how about HG? That would work. Right? It's not intersecting that line and it's not parallel to that. And EF as well. In the back there. GF is parallel, BC is parallel. What about CG? Yep, CG is not parallel and it's also not touching. So that would make it not perpendicular. Right? Anything that touches AD is perpendicular besides this diagonal thing, but I drew that in. What else? How about BF? And is that it? EH is parallel. Could just go through each one, right? FG, FG, FG is parallel. All right, cool. I think we're done. Let's go to number 4. Name all the parallel planes. So this time we're going to look at a side of the box. A, D, C. So the one they want us to look at happens to be the top. So we want to find all the planes parallel to the top. Really, there's only one, right? It's the bottom. So the plane parallel to the top is the bottom. So that'd be plane, you could say E, F, G. We could say plane E, F, G, H. All right, so sometimes these can be tricky. I definitely recommend writing on your paper, grabbing highlighters if you can. But that's it for today, you guys. I will see you soon. I will see you on Thursday. Do not forget, I didn't put this in here, but don't forget that if you wanted to do the gingerbread extra credit, then whether that was you created something or you drew a picture or anything, and that project sheet is in our OMHS extra credit folder. That needs to be turned in to me by today, Monday, December 7th, by, end of day. I don't want you guys building gingerbread houses at midnight, but technically, the assignment will close at midnight. And just email that to me, okay, you guys? Have a great day. I'll see you all on Thursday. Bye, everybody.